Hey guys, sorry for such the late video, and it's like 5 o'clock, and there's no more sun, and I'm in my bedroom, and the lighting is horrible in here, so you got all kinds of funky shadows, and yeah, sorry for the latest stuff. This I got some cool ears on. I don't think they're called like cupcakes and cashmere, but it's kind of cool because it's got these like mermaid scales, so it's like they can go to light pink to dark pink, and oh, they're pink and they're super sparkly and they're fun. So anyways, we are continuing on with functions, and today we're going to be talking about discrete versus continuous domain. And earlier in the year, I was talking about, do you connect this line? And up until now, it's never been a question if you connect when you are graphing points on a coordinate plane. You just connect the points because, it's generally a line. Well, today's the first time you're going to figure out, do you actually connect or do you not connect? And that is the difference between your discrete and continuous domain. So we're going to do 5.2 discrete and continuous domain. So we're going to have some vocab. So my kids, make sure you have out your pink highlighter. So let's get going on this. Try not to wiggle too much. There we go. All kinds of crazy glare. All right, so discrete domain. Now we could talk about the Latin roots of all this, but last time I checked, you guys don't learn Latin anymore. So when you talk about discrete domain, what they are talking about, they're talking about all the inputs that are in a certain interval. Okay, so all inputs, as remember, an input is your x, same thing as your domain, your independent variable. Okay, so all inputs, remember, just your x, that consists of only certain numbers in an interval. Hopefully you guys can read this and it's not too smudgy. Okay, so when we're talking about a discrete domain, we are talking about something like, let's say, when we're talking about an interval, so maybe let's say all the integers from the numbers, let's say 1 to 16. I keep moving that. So if we're talking about the domain, and they're all the integers from 1 to 16, it would be something like this. So it would be the integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It would look something like this. But they would have to be integers. Okay? And I like to use my compound inequalities when I'm talking about domains. Just kind of helps me remember on my guess, you could say. I don't know. So they're looking for very specific numbers. And there's something that will help you when we talk about some problems that will help you understand, okay, is this discrete or versus continuous? So discrete are very specific numbers in an interval. Now, your continuous, if you just kind of think about the definition, I should say, of the word continuous, it just continues on. It's consistent. It's continual. So continuous domain, it's going to be all the numbers. It's going to be all the numbers within an interval. So all inputs, meaning x, within an interval. And the definitions sound almost identical. But this one is the certain numbers, and this is all of the inputs. So we could be talking about something like all the numbers from 1 to 5. So all numbers from 1 to 5. Something like that. Where that could be something like 1, 1.01, 1.02, 1.03, so something like that. If you actually had to graph these would just be points on the number line. This would look like an and kind of thing. Let's do something, kind of looks like a Baymax, 1 to 5, and it would look like this graph. So these would be all the numbers that would be included. Versus up here, you would have just points on those integers. So I don't really have much room here. But let's just say that's 1 in 16. So you would actually see points on the integers. So 1 and 2 and 3 and 4 and 5 and that kind of thing. Maybe I should make this 6. Make that a little bit better. 3, 4, 5. I ran out of room, but I think you guys get the point. It would look something like that. These are very specific points because they're very certain numbers. These are all the numbers, so that's why you have this, what I call the Baymax graph. You know, the 2 dots, because it's including 1 and 5 and shading in between, because it's all of those values in there. One of these graphs you connect when we're talking about a coordinate plane. One of them you do not. Okay. So now we're going to be graphing both of them, and we're going to have to figure out which one we connect and which one we do not connect. So from here on out, guys, when you're in algebra, you've got to really think about if you have to connect or if you don't connect, because then you're talking about, you know, a very discrete domain, something very specific, versus a continuous, which includes just like all kind of numbers. So example 1, we're going to be graphing discrete domain. So when we talk about the discrete domain, we're talking about something very specific. It's almost kind of like you have to pick these numbers kind of a thing. Here we go. So it says the function y equals 15.95x represents the cost y in dollars. So y is total cost of x amount of tickets. So x is the number of tickets for a museum. Sounds good. Graph the function using a domain of, now here they're going to tell you, domain is 0, 1, 2, 3, and 4. 0, 1, 2, 3, and 4. So I talk about the set of numbers that include domain 0, 1, 2, 3, and 4. Very specific. They want you to use these values and these values only. And they want to know, first of all, we have to graph it, and they want to know if this domain is discrete or continuous. So we graph this like, you know, like you do, okay? Double T chart. Here we go. So x, your function in the middle, so 15.95x. Y, I got my phone here ready to go on my calculator. So if x is 0, so that means we are going to buy 0 tickets. So remember, y is the total cost. $15.95 is going to be the price per ticket. And x is going to be the number of tickets. So if you don't buy any tickets, I hope you're not spending any money. So 15.95 times 0, which is 0. And then your order pair of 0, 0 off to the side. And so we want to find out how much we're going to spend for one ticket. So it's going to be 15.95 times 1, which is 15.95. And can you round that up to 16? No, you can't. Because that ticket that you're saying, one ticket, it's $15.95. They're not charging you $16. They're charging you $15.95. So you do the same thing for 2. So 15.95 times 2. So double 16, 32 minus 10 cents, 31.90. My math, I did off the top of my head. Good. 31.90. Okay. Now I'm just plugging through this. It's kind of like you have 5 mini problems. Oh well, at least you know how to do this part. You know. 15.95 times 3. Okay, I'm going to do this on my calculator because I don't want to mess up. So 15.95 times 3. Oops, times 3. So 47.85. So 3 and then 47.85. And you're going to do this last for 4. So what you could do is just double 31.90. 15.95 times 4, double 31.90. Oh gosh, I don't want 63. 63.80. Ha! I was right. Sweet. So when we're working with functions, guys, a lot of the work is still the same. A lot of the work you've already done before, but remember, we're just using the vocabulary, the language of functions to talk about things. So we're talking about inputs and outputs. We're talking about domain and range. We're talking about independent variables and dependent variables instead of saying x and y. Okay, so now we're going to graph all this. I'm going to go to the back. And so when we're graphing this, since we're talking about tickets and real life stuff, look at your domain. Do I need to have X values that are negative? Well, no, you can't even have X values that are negative, other than the fact they told you what the domain to use is. But remember, X is the number of tickets, and you can't have negative tickets. Same thing with Y. If Y is your total cost, I'm trying to avoid this glare here. If Y is your total cost, then you're not going to have any negative Y values because you're saying that's negative dollars. So really what you just need to graph this is Quadrant One. And when we graph this, you always have to make sure you have labels on your X and Y axis. So X axis is going to be the number of tickets. And how did I get that? They told us what it was in the problem. And so Y is going to be total cost. Okay. So our domain is 0, 1, 2, 3, and 4. So let's go up to 5. 1, 2, 3, 4, 5. I'm only doing Quadrant 1. Because you don't need to do all 4 quadrants, especially when you don't have any negative X's or negative Y's. Now, on your Y axis, you need to go up to like basically $64, a little less than that. You do not want to graph them as these increments. You don't want to go by ones because that would be a waste of time. You could do 2s, you could do 5s, but to be honest, I'm thinking 10s would be good. What did they use in the book? Oh, they did use 10s. We'll use 10s. Okay, so let's go 10, 20, 30, 40, 50, 60. 10, 20, 30, 40, 50, 60. And tickets are in ones. Okay. And you're just going to plot your order pairs that you made from the table. So here we go. So we have 0 and 0. Do you have to plot that point? Yes, because they wanted you to use 0 in your domain. So what this is saying, you bought 0 tickets and you spent $0, which should make sense there. Now, 1 ticket's $15.95. So right one and up. So if you're going in between 10 and 20, you want to be a smidge closer to 20 than 10, but basically you kind of want it in the middle. And if we're going by increments of 10, you guys, it's not going to be precise, especially on something like this, because you can't measure that. I mean, you could. You can measure all the spacing in tens. So just make a good estimate. 2 tickets is $31.90. So 2, 3, so it's just going to be a smidge over 30. And then 3 is $47.85. 4, 47. So it's a little bit more than halfway. It's closer to like 3/4 of the way. And then 4 is going to be $63.80. So 4 tickets, 63. I didn't go. Okay. Now, before you just connect it all, you've got to think about this. If you connect, what you're saying is you can have all the values in between these points. Well, pick something that's in between here. So let's say 1.8. Can you have 1.8 tickets? No, you can't. So when you think about discrete versus continuous domain, think about, can you have half of this? Can I have a quarter of this? Can I have parts of that? And remember, your domain is always your X value. So think about it. Can I have half of a ticket? And you can't. So you do not connect this. That's the big question. That's what you want to think about when you talk about discrete domain. Can I have half this? Can I have half a cat? No, you can't. Can I have half a candy bar? Yes, you can. Can you have half of a donut? Can you have half of a Coke? Can you have half of a salad? Can you have half of a person? No, not even like zombie Halloween time. You can't do that. So when you want to think about discrete versus continuous, just think, can I have half of it? So do not connect. And that's going to be really hard in the beginning because you're going to want to just connect it because that's what you're used to. But this is the first time you're going to see the difference between your domain values, the difference between discrete, something very specific, versus continuous. Continuous, you're thinking you can have parts of it. Discrete, you can't have parts of it. Okay. Hopefully that now kind of clears up the definition a little bit. And so we've got to figure out if this is discrete or continuous, because that's the second part of the question. Is this domain discrete or continuous? And since we are talking about a very specific set of numbers in an interval, this is a discrete, this is the other part of the answer, discrete domain. Discrete domain. The numbers in the interval, 0, 1, 2, 3, and 4. That is the numbers in the interval. Okay, very specific. So that's why it's going to be discrete. There we go. And now you're going to do the same thing for example 2, except for now it's going to be graph continuous. Am I going to do all of this? No, because you guys have done graphing. You've done, 3 different ways of how to graph a line. But this is just continuous. So graph continuous domain. Okay, so example 2. A cereal bar contains 130 calories. Okay, 130 calories. Per cereal bar. Okay. The number C of calories consumed is a function of the number B bars eaten. Okay, so C is calories, and B is bars eaten. Okay, graph the function. We've got to figure out an equation. It tells us the number C of calories consumed is a function of the number B bars eaten. So when you do this, you want to ask yourself which one can stand on its own. Can calories stand on its own or bars eaten? If you have a hard time figuring that out, think about which one is relying on the other one. Is the calories relying on the number of bars, or of the number of bars eaten relying on the calories? Well, if you're having a hard time, let's write them both out. So we can go C equals 130B, or you can go B equals 130C. There's 130 calories per cereal bar. You got to figure out which equation is saying there's 130 calories. I'm going to multiply it by the number of cereal bars. That's going to give me the total number of calories. They said calories consumed. So calories consumed. I should put that. So which one is it? Calories consumed equals 130 calories per bar? Or the bars eaten is equal to 130 calories times calories consumed? There it is. Okay, so B is your independent variable, C is your dependent variable. Because the total number of calories consumed is based on how many bars are eaten and how many calories per bar. All right, so now it just says to graph this function, and asking if the domain is discrete or continuous. So since they did not tell you how many, what values are in the domain, you could choose. You can pick. I always like to pick 0 though when I do discrete versus continuous. So I'm going to go the domain. Let's just pick 3. 0, 1, and 2. I'm going to pick 0, 1, and 2 for my domain. Now here's the thing. Could I pick 1.5? Well, can you have 1.5 bars? Yes. Could you pick 2.0985? Yes. I mean, that'd be kind of fun trying to watch you measuring that. But you can't pick that. Okay? These are the numbers I'm going to pick, but you want to pick a minimum of 3. So here we go. We're going to plug it into our double T chart. So X and Y, that's what we're used to. But we are going to be using C and B. Now remember, B is your independent variable, so B is going to actually be your X. And C is your dependent. Because remember, the total number of calories consumed is depending upon how many bars you eat. So that's how you want to think about that. and your function is 130b. We had to come up with this because they did not give us that. All right. So if we have 0 bars, are we consuming any calories? No. 0 bars times 0 calories. Times 130 calories. Well, it's going to be 0 calories consumed because you didn't eat any. So then if you have 1 bar, so 130 times 1. You're eating 1 bar, so it's 130 calories. So 1 bar is 130 calories. And then 2 bars, I think the book used like 5 or 6. Yeah, they used 5 different domains. Whatever. 130 times 2. So 2 bars, 130 calories. You're looking at 260 calories. Okay. Work is the same. Double T-chart. And again, you're going to graph it. So I'm going to graph it on the back. Quadrant 1, make sure you label. So your x-axis, remember, is your B, bars eaten. And your C, also known as your y-axis, is your calories consumed. And the bars eaten, we only did 0, 1, and 2, so maybe like go up to 3, maybe? 4? And maybe we should do 3 and 4. So 3 bars times 3, so 13 times 3 is 390. I'm just doing 2 extra domains right here. And then 4, so we're going to double 2. So 130 times 4, 520. Whoops. Just so we can have more data points, I guess. All right. Okay, so calories. We need to go up to 520. I would do increments of 100. Yep, that's what the book's using too. So let's go 1, 2, 3, 4, 5. I need to probably move my label here. You always have to have labels because I gotta know what that graph means. 100, 200, 300, 400, 500. There we go. Almost done here. So you're going to plot these points 0, 0. 0 bars, you have a total of 0 calories consumed. There we go. 1 bar is 130. So 1 up like a third of the way. 2 bars is 260, so basically kind of in the middle between 200 and 300. Smidge more. You're just going to do your best guesstimate on this. 3 is 390, so that's going to be closer to 400. And then 4 bars is 520. So just a smidge over 500. And the big question is, do we connect? If you connect these, you're saying that you can have half of a bar. You're saying you can have 3 1/3 bar. You're saying you can have 4 and 7/8 bar. Can you? Yes, you can. So you are going to connect this with an arrow. And remember, I draw straight. And we're going to be talking about why this is linear coming up. But just think about it this way. It is linear in fashion because you're going to go up the same amount and you're going to run the same amount. So you're going to go up 130 every single time in between every single point. Because 130, there it is, right there, is your rate of change. Because you're saying 1 bar is 130 calories. That is the part that does not change. So that's how you know that this function is linear. Because there are other functions other than linear functions. We're going to be doing, I think, like 7 or 8 different functions this year. So there you go. So connect. And why do you want to connect? Because you can eat half a bar. That's really what you want to think about the whole time. And they're asking you if its domain is discrete or continuous. This is a continuous domain. There you go. All right. Well, there you have it. I hope now you feel a little bit more comfortable knowing what discrete versus continuous domain is. Just think about, can you have half of something? That's the easiest way I can describe it to my kids. Can you have half of this? Can you have half of that? Can you have half a person? Can you have half of the candy bar? Well, if you answer yes or no, that's basically your answer to discrete or continuous. All right. Thanks so much. Have a good night. Be kind.